All right, so let's see. Now, one thing we want to do today is first let me go over to Moodle and show you what I've put there. Let's see. Okay, so since we're done with chapter 11, I've actually put two problem sets in here for you to work on because, obviously we could all use a little practice here. So you can see they're right there, chapter 11 problems 1 and 2. So what I'd like to do is at least start them on Thursday. We may not have to do them all on Thursday, but at least start, maybe do the first one and possibly as much as the second one as we can, so that over the next couple of sessions, we'll wrap those up. And then in the meantime, we haven't actually, well, we just barely started chapter 12. So I mentioned once before, at least, that the final exam is based entirely on chapters 11 and 12. Now, it's going to be a while. We still have some time left, but we are, of course, getting towards the end of the semester. So our objective going forward between now and the end of the semester is to get the chapter 11 problem sets done, go through chapter 12 and its problem set, and then finally the sample final, which I've already posted right here, by the way. This is, again, all on 11 and 12. When we're done with everything else, we'll go over the sample final, and then you can just do the final and it'll be done. So anyway, that's where we're headed. So these two, download them and take a look. In the meantime, we're going to go back to chapter 12 and get started on it. Now, this one, as I think I've said before, does have a lot of calculations in it. There's also some new formulas that we need to learn. And there's more notation, as a matter of fact, that we need to learn. But you'll see that once you get used to it, it's pretty straightforward. So so again, now you might recall that in the beginning last time, we did at least introduce this concept of populations and samples. And so typically with statistics, we have a population which consists of measurements, not people as such, but measurements about those people. And we are interested in studying them for some reason. Like we might be analyzing the ages of all the people who live in the US, or maybe the incomes of the people who live in Westchester County, or maybe the heights of all the people who live in a certain area, or it could be anything. But whatever it is, that represents our population. And then for the most part, in order to analyze that population, we normally don't look at the entire population because that would take a very long time typically. So instead, we use what are called samples. So a sample is, as you can see here, a subset of the population. In other words, we randomly choose members of the population for our sample, but we have to be extremely careful in the way that we do this. Because if our sample really reflects the population, whatever results we get from our sample should do a very good job of explaining what's going on in the population. So that's the challenge, though, making sure that the sampling is done correctly. Because if it's not, then whatever results we get will be meaningless. Now, this is actually a very broad area of statistics. In fact, if you were actually majoring in statistics, you could take an entire semester of this, sampling techniques, because there's so many of them, and each one has its own advantages and disadvantages. What tends to happen, though, in practice is that certain types of sampling techniques tend to be most useful in different disciplines. Like, for example, in statistics, in economics, we tend to use what's called a simple random sample, where you just basically pick elements from the population completely at random. And whereas with other disciplines, like psychology or biology, where you're actually trying to conduct experiments, the sampling techniques that you use might be very different. Like, for example, what if you're running a psychological test and you're trying to find out what people's attitudes are about, let's say, let's say whether they like chocolate or not, even if it's something that, that basic. In psychology, though, you may want to ensure that your sample contains an even number of men and women. And if that's the case, then you'll be using a very different type of technique than you would if you're just literally randomly choosing people from your population. So there's a lot of different techniques that you might be using. So now I think we mentioned this example. If the US government is trying to find out if the population of Americans is growing in age, in other words, if the average age is increasing, and it could very well be because obviously people are living longer than they used to. And in fact, when the Social Security system was first founded, um, this is an interesting side fact here. The retirement age was originally pegged at 65. Okay, now it's slightly higher, but it was originally at 65. The average American now apparently lives to something like 77 or 78 or something along those lines. So a typical American can expect to be retired for, let's say, 12, 13 years. But when the system was first invented in the 30s, the average life expectancy was only 63. So that meant that they were pegging the age at 65, knowing that the average American only lived to be 63. So they didn't expect a whole lot of people to actually collect on Social Security when they first created this system. And now it's, well, people are living so long that many people collect Social Security. And so if that trend continues, they will need to find other ways of financing it. So the government is doing a study in this example to find out if Americans are living longer than they did, even as recently as 20 years ago. So how could they go about studying this situation? Well, they could literally get everybody in their, they could look at the entire population, which is over 330 million people, and that might be a bit intimidating. So instead, you could just take a long time. Even if they have the information in their computers, it could take a very long time to analyze this kind of data. So what they'll probably do instead is they'll choose samples, and they pick them carefully enough, they should have an accurate reflection of the ages of all Americans in the United States. And then whatever results they get from their sample should tell them roughly whether or not Americans are living longer than they did 20 years ago. And that's all they need to know. Yes or no. Like, in other words, imagine the average age has gone up from 75 to 77. That's the kind of thing they need to know, because that means they'll have to spend more money on Social Security in the future, and therefore they have to figure out ways to finance it. All right. So in this example, suppose that they picked 100,000 people randomly scattered across the country. Again, if they've done it carefully, that should be a very good reflection of the underlying population. Oh yeah, we had this example with Coca-Cola and Pumpkin Coke. Marketing is kind of an art where, you know, these different companies need to know how people will react to their products. So they usually hire marketing companies to take care of this for them. And then they'll say, listen, find out if people like this new flavor or not, or this new product that we're producing. And so how do they do that? They have to ask people. The question is, how do they choose the people that they ask? That could be a real problem. If they don't do this well, they'll end up with a disaster on their hands. And in fact, that reminds me, there's a very interesting scenario where something went horribly wrong about, wow, it's a while now. Let me go back and double check. It was the 80s, I think. No, maybe it was 85. Okay, so imagine the following scenario. This is a case where sampling was not done well, or at least the procedure wasn't done well in the early 80s. Okay, so this is how not to conduct marketing research. Okay, so here's a case study which shows you how not to go about doing this. And it turns out the Coca-Cola company was involved. You would think that they would know better. They could afford to hire the best researchers in the world. And this is what happened. Now, this is in the 80s. So remember, they haven't yet brought out a lot of the new flavors that they have, like Coke Zero and you know, all these other variations of Coke. At this point in time, basically all they have is the basic Coke and Diet Coke. That's it. They have other flavors from companies that they bought out, like Dr. Pepper and that kind of thing. But so they're looking to expand their product offerings. And here's the thing, though, that they were worried about. The Coca-Cola company was concerned that they were losing market share to PepsiCo. Of course, who's their main rival? Okay, they suspected that their flavor, that Coke was not sweet enough for the general public. So here's what they did. They developed a new flavor called New Coke, which was slightly sweeter. They then did test marketing to determine if consumers preferred New Coke to the classic Coke, I guess you could call it. Now, here's the interesting result. Now, the results showed that most of, I don't remember the exact percentages, but most of the people who were tested said that they preferred the New Coke because they liked the sweetness. In other words, they're trying to find out if the slightly sweeter version was something that people preferred to the traditional or classic Coke. All right. So most of the people, actually, let me change this to traditional. Most people said, yeah, sure, we like the New Coke a little bit better than the existing one. So what did they do? Now, this is where it gets strange. As a result, and this, Coca-Cola decided to stop selling the traditional Coke and replace it with New Coke. Now, this is where the problem comes up. No one in the test who was tested was told that if people preferred the New Coke, that the traditional Coke would disappear and be replaced with the New Coke. In other words, they thought that what Coke was planning on doing was adding New Coke as another option. But instead, what they were planning on doing is taking the old Coke off the shelves and completely replacing it with a New Coke. And so because of that, when they decided to go ahead and actually do this, once the New Coke came out, the public was so furious that Coca-Cola had to backtrack and reintroduce the traditional Coke under the label Coke Classic, as if they're trying to pretend that was what they meant to do all along. In other words, they were trying to cover their butts here by saying, oh, wait a minute. No, you misunderstood. We really were just trying to bring out the New Coke and then bring back Coke Classic. But of course, nobody was conned. And so the company lost tons and tons of money. I mean, this is like the worst public relations nightmare you could imagine, taking a classic, iconic product like Coca-Cola and just removing it from the shelves. It was, let's say, it couldn't have been a bigger disaster. So, well, now, eventually, what they did was, when the uproar died down, the New Coke was removed and the traditional Coke was relabeled again as just plain Coke. Okay, so in other words, now they were back to what they had before. In other words, there's no New Coke anymore. Instead, we have regular Coke, but it's called just Coke, not Coke Classic. So naturally enough, many people were fired over this, and the company lost a boatload of money. But see, the thing is, it was their own fault because that was really the problem. By not telling the customers that they were testing what their intentions were, that if people really thought, well, here's another option that they'll offer to us, that's fine. I like it. It's not bad. But because they weren't told, oh no, this is meant to be a replacement for the Coke, if that had been told to these people, most likely their answers would have been different. And so they basically shot themselves in the foot. And in fact, this case study is still studied in MBA schools all around the country. Even here it is nearly 40 years later. This is presented to MBA students as a classic example of how not to do marketing research. It's not, the problem wasn't really so much that they chose bad samples, which is kind of, you know, I don't think that was a problem. I think it was just the way they conducted the actual research by being careless about what they told the people that they were testing. They basically made sure that this was going to end very badly. So anyway, so I just wanted to throw that in there just as an example of how sampling and marketing and research can go wrong. Not necessarily just because of the way the samples are chosen, but because of the way that research itself is conducted. In fact, if you want to go to the internet and read more about this, under New Coke fiasco, it's all there. See, New Coke. Then they pulled the plug on it. Well, actually, they left it out there for 7 years. Yeah, but eventually, they realized, well, we better do something about this. So anyway, but then of course Pepsi had a lot of fun with this. So anyway, but let's just say that they hope that nobody else knows about this. It's been a while. They recognize that most people don't remember any of this. They're too young to remember any of this, and it shouldn't matter anymore. But it's still a black eye for the company, especially a company that was so proud about their marketing capabilities. They really blew it this time. But anyway, so now it turns out the next section we're going to be looking at numerical measures that help us understand the key properties of a set of data. In other words, whether we're looking at a population or a sample, just having all that information is very difficult to analyze. What we often like to do is create a series of measures, as they're called, which help us understand the most important properties of our sample or population. And these are all collectively known as measures of central tendency. And so what they're trying to help us identify is the center of the data. In other words, what values would fall in the middle. And for a lot of applications, that's an important piece of information. Like imagine if you hold a portfolio of stocks, you might want to know what is the average rate of return among all the stocks in my portfolio. That could be considered a measure of central tendency. Now, it turns out that there are three that we would like to focus on, and there's a pretty decent chance that you've heard of all three of these, but you might not remember what they mean. I know that some high schools do teach statistics, or at least they try to introduce it to you, and others don't bother. But they are mean, median, and mode. Now, most likely, certainly you've heard the word mean before. Median and mode might seem familiar. What we want to do is understand what they are telling us and how they are calculated and when each one is appropriate to use. All right. Now, in the course of doing this, though, we're going to introduce some formulas, which gives us an opportunity to introduce some new notation. Now, luckily, the calculators will be very helpful with what we're about to do. All right, so why don't we start with the mean? Now, in statistics, there are many cases where there could be multiple words that mean the same thing. So here's a perfect example of this. The word mean is simply an alternative version of the word average. Everybody knows what an average is. So just be aware the word mean is simply the same thing as an average. Median, well, we'll get to that in a couple of minutes, and mode. Of the three of these, the one you see the most frequently is the mean. Okay. Now, everybody intuitively, I think, knows how to calculate an average. If I wanted to know, for example, the average commuting time of all the students in this class, I would write down for each person what your commuting time is. I would add them all up, and I would divide by the number of students in the class. So intuitively, everybody knows what this means, but we want to formally identify the procedure that's being used to do this. And so we'll start by observing that the formula for calculating the mean of a sample is this. Now you can see it looks scary, doesn't it? When we're done with this, by the way, we're also going to introduce a formula for a population mean. So for this case, we will need two separate formulas, one for samples and one for populations. Now, here's the big question. What do all these symbols represent? Now, you may have seen these before, and maybe you have not. This X with a little bar on top of it is pronounced as X bar. And whenever you see a little bar like that in statistics, that tells you that you're calculating an average. Okay, so the bar is used to indicate this is an average. This is standard practice in statistics. Now, N on the denominator is the sample size. In other words, how many elements are in your sample. And then we get to the interesting part right here on the numerator. X with a little I represents a single element. In the sample. Now, what exactly is that I doing there? I is what we're going to call an index, which helps us keep track of the elements in the sample. So let's say you have 3 elements in your sample. Let me jump ahead to the next slide for a second, just to show you what this would be all about. And this could be done in a lot of ways. Suppose that a sample consists of the prices of the Starbucks of a coffee. At let's keep this simple, 3 Starbucks. Let's say let's imagine that you're in the Mall of America in Minneapolis, the largest mall in the country, by the way. And let's say the place is so big that it has 3 Starbucks in it. It's so big that you don't want to walk a mile to get to the next Starbucks. So they have 3 of them. And so the first one is $2. The second one is $2.10. And the third one is $1.95. So what these are telling me is that the first Starbucks charges $2. And, any one of them could be defined as the first Starbucks. Let's say it's the first one that you see when you walk in the door. And then the next furthest one away, the second Starbucks, is $2.10. Let's say they charge $2.10. And the third, the one that's furthest away from the front door, charges $1.95. So the index, as you can see, this little number here tells me which Starbucks I'm referring to. So that's why that's there. It helps me keep track of which element I'm referring to. Is that the first Starbucks? Is that the second Starbucks? Or is it the third Starbucks? Now, by the way, is anyone here from the Philadelphia area? Or nearby there? Or maybe that portion of Jersey that's near Pennsylvania? I just wanted to mention, the Mall of America is in Minneapolis. You're not likely to get there anytime soon. But if you live in the Philadelphia area, the second largest mall in the country is in a town called King of Prussia, which is in the outskirts of Philadelphia. So if you're into malls, I mean, if you love malls, gigantic malls, and you're in the Philly neighborhood, you can go to King of Prussia and visit the second largest mall in the country. I've been there. It's big. It's big. You literally can get lost in there. There's so many twists and turns. There's so many avenues going up and down, and there's 3 or 4 levels, and it's enormous. It's the one time in your life you might seriously think about bringing a map with you. It's that big. It's like a small city. I mean, really, that's how big it is. And I can easily see them having 3 Starbucks in there because it's just so scattered out. Anyway, so that's what those X's are. So the I is just meant to be the general expression for a single element. Now, if you look at over here, the I, this tells us that the I ranges from 1 to n. So in other words, this is a shorthand notation for saying I can take on any value from 1 up to n, whatever n happens to be. So I'm saving the best for last. This very mysterious looking symbol is actually a Greek letter, and it's called sigma. Specifically, it's the uppercase version of sigma. The Greeks had case just like the Romans. That's why, and we of course have case as well. This is the uppercase sigma in the Greek alphabet, but what in the world is it doing there? It has a very specific mathematical interpretation. It's called, okay, I'll give you a minute to catch up. It's called the summation operator because it is telling you to add up a bunch of numbers. In fact, that's why it was chosen, that letter, because this corresponds to S in the Roman alphabet. So S for summation. So in this specific case, it's telling us to add up all of these elements in the sample. Okay, in other words, add up all the elements in the sample. That's what it actually means. Add them up. It's just a very compact way of saying however many elements there are, what you're going to do is add them up. Okay, so I've got a somewhat more detailed discussion here coming up of what the summation operator is. So let's take a look at it, or how it works. That's what we really want to know. How does this thing work? All right, so suppose I give you a sample of 5 elements. Now, if you notice again, they all have an index. So there's 5 of them, and we need to be able to keep track of them. So now it doesn't specify here what they represent. It could be anything. Suppose that, let's say these are temperatures in Celsius during the first week of January. Let's say we go outside every day from Monday through Friday, and we take the temperature in Celsius. So 2 degrees Celsius is like 35 degrees Fahrenheit. So you can tell this is Christmas time. So the first 5 days in January, you go outside with your thermometer, you take the temperature, you write it down, and you now have a sample of 5 elements. Now it's a sample because the population would consist of all the temperatures throughout the entire history of the area that you live in, going all the way back, I suppose, to the Big Bang. That would be a big population. So this is a sample, and you'd like to use that information to understand what the average temperature looks like in your hometown during the first week in January. Now, obviously, if you keep taking different samples, you'll get slightly different numbers, but this is the sample that you have. So the summation operator applied to these numbers would mean that what you're actually doing is this. So formally, you're writing it out as x1 plus x2 plus x3 all the way out to xn. In our case, there's 5 elements. We add them up and we come up with a 10. But in general, for no matter how many elements you have, this notation tells you to add them up. So you can see why it's so useful, because this takes a long time to write, especially if you, let's say you have 500 elements, this would take forever. So instead you write it like this, and you can see it saves a lot of time. So that's what that summation operator would actually mean. Take the numbers and add them up. So let's go back to the original slide where we were looking at this. And what you'll discover is that in the formula for X bar, now that you know the secret, what this thing means, you'll see that the formula is very simple. You see what it's saying? In the numerator, add up all your elements. In the denominator, divide by the number of elements. And that result will give you your sample mean. And this is the part that everybody, I think, intuitively understands. A sample is just a sum of elements divided by the size of the sample. So what went from 5 minutes ago, a frightening looking formula, has suddenly become very simple. Add them all up, add up all your elements in your sample, divide by the sample size, and you have your sample mean. It's just that simple. All right. Now, it turns out, though, one of the nice things about the summation operator is that it can be extended to do more complicated calculations, which we will need in some of the formulas that we'll see later on in the chapter. So it's more than just a simple addition. There's other things that can be done with it. So let me show you some of them. And these are the only reason I'm showing them to you is because we will need them, not because of the fun aspect of it, although it certainly is fun, but just because we'll need these down the road. What if I did this? What if I wrote not the sum of x's, but the sum of the x squares? Ooh, now something is very different, isn't it? What you're doing here is you're not adding up the x's, but the squares of these x's. Okay, so here you have to square each one, and then you can add them up. So in our case, with our data, our temperature data, you see what you have to do? You have to go through and square each one, and only then can you add them up. All right. So it's a little bit more challenging, but still conceptually, it should be pretty clear what you're doing. And now if you notice too, because we're squaring them, the sum is not 10 this time, it's 40. So it's a very different outcome. Wow. So already you can see another impressive thing that this summation operator can do for us. Oh, one more thing, I do want to mention this, that sometimes as a shorthand, while you theoretically should write the index on here, sometimes if you're reading in let's say in a math book, you might see it written like this, where there's no index. It's, in other words, it's sort of implied by the way it's written. So you might see this, it means the same thing. I just want to point that out as we go along. If you see the summation operator without the indexes, it's implied. It's supposed to be there, but sometimes as a shorthand, we see it left out. All right. Here's another example. Now, this one is really tricky because look what's happened. Instead of this, all right, let's go back and look at this one again. Here we have the sum of the x squares. This is different because the entire sum is being squared. So we add the numbers first. And then square the result. Whereas back here, each element is squared. I'll just add this in here as an explanatory note. Before they're added. And so that's, you can see this is different because we square them and then add them up. Whereas in the next slide, it's the other way around. And you can tell because of the placement of the parentheses that the second case is different. Okay, so in other words, you see here, the sum is in the parentheses. Therefore, we do all that first, and only then do we add them up. Only then do we square them. So this part is the same as we had before. We add them all up to get a 10. We square the sum, and we end up with 100. All right, is there anything else that we could do here? Yes, there's one more case which is fairly involved, but again, we are doing this only because we need it, or we will need it. Well, you probably are asking yourselves, what else could there possibly be? Oh, yes, there's more. But if you get what we've done up to this point, it should not be a problem. Now look at this disaster. Ooh, now this k is a constant. It could be anything, 3, 7, it doesn't matter. So what you have to do here is this. For each element, subtract k, then square the result, then add up. And you'll see an example in the next slide. And then once you've done it once, you'll say, ah, that's not so bad. So I'll give you a minute to copy that down. And then we're going to do an exact example using the same data set that we've used up to this point. We're going to do this with a constant. So So let's try 3 as our constant. Okay, so what's going on here? We've got, remember our original data was 2, -1, 3, 5, and 1. So what I'm going to do is go through each one and subtract 3. You can see down here, I'm subtracting 3 from that element of x, and then I'm going to square the difference. Now, in the next row, what I did was I actually calculated the differences first, just to avoid making mistakes. And then I've squared them all, and only then at the end have I added them up. And you can see that the result is very different than what we've had earlier. All right, so that's the last one, by the way. We won't need any more of the more advanced applications of the summation operator, not for this class. If you find yourself in a full statistics class where you just do statistics all semester long, well, then you'll need this more often. But for now, that will suffice. Okay, I can hear the cheering through the screen. All right, so now that we understand how the summation operator works, most of the remaining formulas that we'll be seeing involve the summation operator, okay? Because with statistics, whatever we're doing, we have to do it to every element in our sample or our population. All right, now all of that enables us now to come back and revisit our discussion about the sample mean. Specifically, we'll go back and revisit the formula that we saw and see how that leads us to our final result. All right. So in the numerator, we add up our elements, which we already knew was equal to 10. In the denominator, though, we divide by 5 because there are 5 elements in the sample. And we end up with 2 as our average. Now, this is easy to do on your calculator. The only thing you got to watch out for is that when you're done with the sum, make sure there's an equals at the end. In other words, add them all up, make sure it says 10 in the window, and only then do you divide by 2. All right, so that's how the sample mean works. So you know what, why don't we make up a completely new example before we go on, just to make sure that we get it. Suppose that a student has taken 4 exams during a semester, and the scores were 80, 90, 92, 99. What is the student's average? Okay, so you can think of these as x1 is 80, x2 is 90, x3 is 92, x4 is 99. What are we going to do with this information? Well, we already know the next bar equals the summation operator divided by n. So we're going to actually do that right now. So we'll have All right, I'll repeat the values here because we'll need them. So first, why don't we do the summation operator? Oh, I'm running out of space. Okay, much better. All right, plus 99. And when you add those up, they add up to 361. Also, n equals 4 in this case because there's 4 elements in the sample. So therefore, x bar must equal 361 over 4, which equals 90.25. So the student's average for the semester is 90.25. And it's a simple matter of adding up all the elements and dividing by the number of elements. So all the sample mean questions you'll ever encounter are done in exactly the same way. All right, now I mentioned earlier that in this case, at least, we will need a separate formula for calculating a population's mean. The formula actually it works the same way, but the notation is slightly different. So I'm going to show it to you on the next slide. We don't need to do a separate example because it's the exact same procedure, but we do need to know what it looks like. All right, so let's take a look at this thing. There's really 2 major changes in the formula. Okay, so let me remind you what the sample version looked like, just so that you can compare them side by side. So first things first, if you notice, instead of x bar, what is this? This is the Greek letter. This is the Greek letter mu, it's called. It's the Greek equivalent of M in the Roman alphabet. And we use this to represent the population mean. And then the other change is here. Capital N will be used from now on to represent the size of the population, as opposed to lowercase n, the sample size. Now, here's an important, I'll give you a second to catch up. Just as far as the notation is concerned, I'll just throw this in here. Note, and you'll notice this pattern as we go through the chapter, we will use Greek letters to represent population measures and Roman letters to represent sample measures. So that's why we're using a Greek letter to represent the population mean, whereas of course the sample mean X bar, X is of course a Roman letter. So that's the strategy that we'll be using. This is standard notation in statistics. Greek letters, again, are meant for populations, and Roman letters are meant for samples. I don't know how this came about, but over the centuries, this is what people started to do. And so it has become a convention that we always follow. Okay. And of course, you know that a lot of the early results were derived by the Greeks. And so, although their focus was primarily on geometry, a lot of the later results were developed in the Middle Ages. Some of that while the Roman Empire still was intact. But even after the Roman Empire was gone, most scholarly material was written in Latin. Okay, so for the longest time, Latin was the main language, even after the Roman Empire was gone. So a lot of the results in math, for example, were written up in Latin. In fact, even Isaac Newton, who invented calculus, he wrote in Latin too, because at the time that was considered to be the language of the educated. All right, so that's why so much of what we have is written in terms of Latin. All right, well, anyway, so now what we're going to do now is look at a slightly different variation of the mean. We're going to look at what's called a weighted average. A weighted average is used when some observations in a sample or population occur more frequently than others. It's actually more than anything a shortcut, but it's useful when we have a lot of values that repeat over and over again. So you'll see what I mean in a minute. Okay, now look at that formula. Ooh, boy, doesn't that look scary? It's only slightly scarier than the first one we had. But what's different here is that each X has a weight associated with it. So in other words, WI is the weight of element XI. So for each XI, we will multiply it by its own weight in the numerator, add them up, and in the denominator, we add up the weights. So in the numerator, each element, or each XI, is multiplied by its weight, and these products are added up. Down here, the weights are added up. And of course, you notice here we're still using, we're using X bar here because this is a sample that we're looking at. So it's a mean, it's still a mean. It's a different kind of mean, but it's still a mean. So we're going to continue to use the notation X bar to represent the weighted average or weighted mean of a sample. Now, it turns out that there's an equivalent version that's used for populations. So why don't we just look at them side by side and again, see where the differences are. You know what I'll do? Let me copy this one so you can see them side by side. And so there's really only two differences. Where are they? Well, we're once again using the Greek letter mu instead of X bar, and we have capital N's instead of lowercase n's. Other than that, you can see you're doing the exact same thing in both cases. All right. Now, we're ready for an example. I'll give you a minute to catch up. All right. Now imagine the following situation. We have a lottery. It's a small lottery. The prizes are not very big. Let's say it is a White Plains lottery or something like that. The city of White Plains has its own lottery. And the lottery provides one prize of $1,000. Not exactly, Powerball, but there's $1,000 prize, 10 prizes of $500 each, 100 prizes of $10 each. What is the average prize received by a winner of this lottery? So if you do win, on average, what would be your prize? Now, what we cannot do here is simply take those three numbers and add them up and divide by 3. So let me just point this out. Let me just leave this up for a second so you can catch up. But I'm going to show you that you cannot, in order to come up with this answer, simply combine the 3 and then divide by 3. The question is, why not? All right, so in order to obtain this answer, or to find the average prize, we cannot simply add up 1,510 and then divide by 3. This would only work if there were an equal number of each prize. So if there were 10 prizes each, you'd be fine, but it didn't work out that way, did it? Instead, the number of prizes of each value is different. So we must use a weighted average to come up with the mean. And it should make sense. I mean, we've got so many $10 prizes and only $1,000 prize. Of course, we have to take that into account somehow. And that somehow is to use a weighted average. All right. So, I think it should be pretty clear. We would never just add those 3 up and divide by 3 because we don't have an equal number of them. We've got way more $10 prizes than $1,000 prizes. Now, what we're going to do here, and each time we do a weighted average, the weights themselves can be defined differently. Here, in this case, the number of prizes will be considered the weights. Okay, now it doesn't have to work that way, but this is one way we can come up with weights. The number of prizes will be considered the weights. So that being the case, remember the formula requires us to know all the X's and all the W's. So we're going to put together a little chart in which we list them all out. So then you can easily calculate the weighted average. All right. So here's what I mean. So if you notice, the prizes, the X's are the prizes themselves. Okay, so we got three prizes, 1,510. The weights are the number of prizes with that value. So there's only $1,000 prize. Therefore, that's the weight of the $1,000 prize. There's 10 $500 prizes, and then there's 100 $10 prizes. So the average is going to be a lot closer to 10 than 1,000 because there's so many $10 prizes. The question is, what is that average? In this case, we're going to treat the three prize values as a population because that represents all the prizes that are available in this lottery. So we're going to use the population formula this time. And so the calculations are shown in the next slide. And we're going to just do some substitution. What you should do is try to make sure you can reproduce these results with your calculator. So here's what I mean. These are the W's. Now, based on the last chart, this is W1, X1, W2, X2, W3, X3, W1 plus 2 plus 3. That's where these numbers are coming from. And I'd also like to point out, I should have done the calculation separately, but in the numerator, you've got 7,000. And in the denominator, you have 111. And if you plug that into your calculator, you'll get approximately $63.06. So if I win the lottery, on average, my prize will be $63.06. Now, of course, it sounds a little strange because there isn't a prize worth $63.06, but every time I win, I might get 1,000, I might get 500, I might get 10. On average, that works out to $63.06. All right, so I hope you'll see the idea. Now, there's a classic example here that I'd like to show you of when weighted averages are used, and you may not have noticed this going on behind the scenes, but it turns out that at the end of the semester, when they calculate your GPA, that's also the result of a weighted average. Okay, so let me show you how and why that works. Okay. Now, having said that, where's this coming from? Everybody knows how the grades are calculated. A is a 4, for example, B is a 3, C is a 2, et cetera, et cetera. Where the weights get involved is the credits. Now, most schools, the courses are all worth either 3 or 4 credits, depending on how many hours you meet and other issues. And often you'll have a mixture of both in your schedule. It's very unusual that somebody gets through their whole college career only taking 3 credit courses or only 4. And if you're involved in science classes where there's a lab involved, you might even get 5 or even 6 credits for that. So how do they figure out your average then? Well, let's look at an example. Like I'm assuming this class is worth 4 credits because it's math, and math is hard. All right. So here's another example. All right. So here we're going to have a table showing for a student 4 classes, and they're going to have, let's see, we need 3. Oh, this is one of my pet peeves about Microsoft products. The choices, the default colors are often very bizarre. So we're going to have the class, the letter grade. Actually, you know what I'll do? Let me have a fourth column here. That should do it. And then credits. Okay. Now, of course, this is completely made up. This is not a real person. Hold on. Let me see if I can make it bigger. All right. Suppose that the first one is this is a tough schedule, pre-calculus. And the student gets a B, which is worth 3.0 points, and it's a 4-credit class. Okay. Or, yeah, that's fine. English 101. C plus. Okay, 2.3, 3 credits. How about this one? The history of Western civilization. The student gets an A minus, which is 3.7, 3 credits, and then they take physics. They get an A, that's a 4.0, and that's a 4-credit class. Now the question is, what is this student's GPA? Well, in this example, what we could do is, you know what I'm going to do? Let me just steal this table and add two more columns to it, just so you can see everything all together in one place. So what I'll do is at the end here, I've got plenty of room. I don't actually need the letter grades for what I'm about to do, but I want to keep them all together in one place. What I'd like to do is show you where are the X's and the W's. All right. Oh, that's not what I wanted. So I'll introduce 2 new columns. Man, this thing is really being a pain. Oh, I know what I can do. I just realized I don't need to leave it. Yeah, I can fit it in here. Okay, I think we're looking good. All right, so what I wanted to indicate here is that these are the X's right here. Actually, let me do this. It might be even more meaningful. No, it doesn't like that. All right, let's try that again. What I'm going to do, just because I want you to see the connections, these will be the X's, and these will be the weights in my calculations. Well, all right, it's being too much of a pain. I'll just leave it like that. X1 will be 3. W1 will be 4. X2 will be 2.3. W2 will be 3 for 3 credits. X3 is 3.7, and W3. Okay. See, the thing is, it has a mind of its own. There's a way we can fix this. Watch this. If you've ever used PowerPoint, you know that it tries to take control sometimes. And so the way to get rid of that, so go to Options, Proofing, Autocorrect Options. Here we are. Just tell it to stop doing that. So in other words, don't worry, I'll take care of that. You just you let me do the thinking, okay? So you see it's not doing that. It's not capitalizing it on me. Yes, I basically told it to stop doing that. Okay, I will take responsibility for getting that right. All right, so finally, it's done. So how do we figure out the student's GPA? Just like we did in our weighted average example. Okay, so if I copy this formula, I can just edit it with the new information. And this, I'll treat this as a population again too, because this, my semester grades, let's think of it as a population. So I'll have the weight of the first class is 4 credits, and that's the B that I got in pre-calc. The next class is 3 credits, and that's where I got a 2.3 in English 101. Then I have another 3 credit class where I got an A minus in Western Civilization. And then I have 4 credits in my physics class. Down here, the weights are the credits, so I'll just have 4 plus 3 plus 3 plus 4. Now in the numerator, if I take out my calculator, I'll have, let's see, $46 is divided by 14. And so after all that work, my GPA is approximately 3.29. Not bad. I'll take it. All right, then I just have to tidy it up a little bit. All right, and there it is. So in other words, this is another example of a weighted average. Because all the credit hours in your classes are not the same, we need to calculate your GPA as a weighted average instead of just adding them all up. Like here, you would not just add up these 4 numbers and divide by 4. You would get the wrong answer. Okay, so this is how, whether you knew it or not, this is how they're calculating your GPAs. All right. If you ever wondered how they came about with these numbers, this is what they're actually doing. Okay, so I thought you'd find that interesting since it's directly relevant to what you're doing in school. So there you go. So anyway, so already you can see a useful application for weighted averages. Even if you never play the lottery, you certainly have a GPA that needs to be calculated, and that's how it's done. All right, now remember way back in the beginning, we said that there were three measures of central tendency that we would like to investigate here. The second one is called the median. Now, the median is not used quite as extensively as the mean, but there are certain cases when the median is actually a better choice than the mean. So let's first see what this median is all about. The median is a number that splits our sample or population in half, in the sense that half the values are below that number and half are above. So let me show you what this would mean in practice. Suppose that I told you, or suppose that the median age of all Americans is 28. This means that half of all Americans are 28 or below. Half are 28 or above. So it's the dividing line between the bottom, the youngest, and the oldest. It's the halfway mark. Suppose that the median score, I'll move this to another slide. There's no way I have enough room here. All right, this one will be more directly relevant. Suppose that the median score on an exam is 82. This means that half the class had an 82 or below. Half had 82 or above. It's the dividing point, half. Okay. So now in general, how would you calculate this given a set of data? So let's go back to the data we had before. Now, in a case like this, you can look at the data, maybe figure it out, but typically the first thing we want to do is sort out the data from the lowest to the highest. So let's do that. If you sort them out from low to high, you'll have, here we are. The median is the halfway point. So when we have an odd number of values, what we do is we define the median to be the value in the center. So out of all these temperatures, half of them were 2 or less. Half of them are 2 or above. Now, that was easy, but what if we had an even number of values? What if we had not 5, but let's say 6? Then there's not going to be a single element in the center. What do we do then? Oh, good question. All right, so let's go on to a new example where we have a different element sample that has 6 observations instead of 5. So what we'd like to do this time again is sort them out from the lowest to the highest, and then we have to figure out what to do to calculate the median. And again, these could be temperatures, let's say in the beginning of January, right after Christmas. So this time, what we're going to do, well, first, of course, we sort them out. But then, because there's not an odd number of values, what we have to do is, as a compromise, we average out the two that are in the middle. And in this case, that would be 2.5, which you can see cuts the data in half. 3 are below, 3 are above. So even though 2.5 is not even in our sample, we can think of that as our median value. It's the dividing line between the ones below and the ones above. All right. Now, unlike the mean, though, there is no formula for doing this. Okay, so if you notice, we didn't actually use a formula. So for the median rather, there is no mathematical formula. Instead, the calculation of the median follows a set of steps, which means sort the data, find the value in the middle. Basically, that's it. So there's no formula. What formula? You can't really express this as a formula. And in addition, so that means, oh, and one more thing too. Another point that we want to make is that for the median, or the sample median and the population median, are calculated in exactly the same way. So in other words, we don't need to make a distinction between the two of them. The median is the median. It's done the same way, regardless of whether we're looking at a sample or a population. So there's no formula, and there's no distinction that needs to be made between the sample and the population. All right, now the next section, which we won't have time for today, basically explains let's say the pros and cons of using the mean and the median as our measure of central tendency. This is a fairly involved discussion. So we'll stop right here. We do not want to carry on past this point. What I do want to do is remind you that you should, between now and Thursday, take a look at, okay, I lost my Moodle here. Take a look at the 2 Chapter 11 problem sets. Oh no, here it is. Those will give you tons of practice about probability theory so that we can eventually, of course, take the final exam based on 11 and 12. So we'll do those first on Thursday. And if there's any time left, we'll get back into our discussion about the mean versus the median. Okay, so that's where we're heading. We want to understand how and when you would choose the mean and when you would choose the median as your measure of central tendency. All right, so other than that, I guess we're done.
Thank you.
Thank you.
Thank you.
See you next time.
Thank you.
Bye.